Around 2 years ago, I made a project called Coda. It was an interpreted programming language. What's fun thing about Coda is it was 8 times faster than Python and approximately 3 point faster than JavaScript. When I was making the language, there were no good tutorials or good length tutorials with C++. There were few tutorials which had around 10 to 12 hours of content, but it was too large for consumption. And there was tutorials which were short, good, but they were not in C++. They were using a dynamic programming language. For example, Python or TypeScript, something. So I decided to view the tutorials and write my code in C++. So I was watching the tutorials in Python and was converting the code into the C++. It is a little bit difficult to do that because of the types, and people tend to ignore all the safety things in Python or JavaScript. Building this language taught me a lot of things, and because it took me a long time, I documented it into a book. Many of you might have read about this book. So this book is just a compilation of the project Coda, and it has all the things necessary to make a programming language. There is a lot of diagrams, there is pseudocode, and most of the theory covered. When you write code, it has to be converted into machine instructions for computer to understand. It can't directly understand what you have written, so we need an intermediate step to convert this. There are two methods of doing this. One is compiling and other is interpreting. What compiling does is it converts your code into instructions while you are developing or while you are building. There is a build step in between. So what happens is when you write the code, you build it into machine instructions and then you directly run the machine instructions. This is called compiling. There is another one which is interpreting. So what we do is we keep the source code as is, and when we want to run the code, what we do is we pass it to an interpreter. What it does is it reads the code line by line and converts it into a machine instructions at the time of executing. So running a compiled code is faster because all the compiling is done before running the code, and interpretation takes time. But because of interpretation, we don't have to necessarily have types for our variables. There is another step, another type we use is transpiling. So what it does is converts one code from a given language to another language. For example, there are transpilers for converting TypeScript code into JavaScript code. This is another method, but this is not what we are going into. Compiling is also not what we are going into, but this concept which we will be covering will be applying for both of this and maybe even transpiling. There are multiple steps before we run a code. These are tokenization, which in which we convert a plain text or character array into a tokens. Then there is parsing, in which in parsing we generate an abstract syntax tree. We will cover this later. And after generation of the AST, we interpret the AST to find the answers of our lines. So this is the basic thing which we need to know about running a interpreted language. Now, what is this tokenization? Tokenization is an important step in converting the code into something which we can run or which we can evaluate. Why tokenization? We will get code in the form of strings. So this will be a single string with all the code in it. Now, to understand what the code is, what one can do is run a for loop and check if there is an int, and then there is a space or x, then variable, then there is again a space, then equal to sign. You can check this, but then after checking, it's difficult to interpret what the thing actually is. Let's say this int is representing something else and this int is representing something else. This is a type of x, and this int is the return type of the function add. Both are almost similar but have different purpose. This int represents the type of the x, and this int is just the return type of the function add. So while, let's say, you are an interpreter and you want to assign some value, let's say assign some space for your variable x, what you will check is what type it is. You without tokenization, what you would need to do is go through and check if this is a variable. So you will find all the keywords present in your language, check if it matches this X. If none, you will call it as a variable and check and find its type. What we will do is we will ignore the space and we will find what is written behind it. So in this case it is int, so integer. But this is a little bit unintuitive because there are multiple spaces. Let's say if there are two spaces, how will you understand? That's why we have a tokenization step in between. Let's say we will try to tokenize this first line. So how it will tokenize is, let's say we found I, we found N, we found T. Okay, we know that int means integer and it is a type. So we'll create a token for it. It will be a type token with value int. Then there is a space. We will ignore spaces because spaces don't matter. Then there is a letter X. Now this is not a keyword. It is not a keyword from a language. So it might be a variable. For now, we will call it as identifier. So we will call it identifier and it is X. Then there is again a space which we can ignore because again spaces don't matter. Then there is an equal to sign. We will convert it into again a token. It will be a sign token. Let's say equal to. And this way we can make multiple tokens after the equal to sign. There can be any number of spaces and there can be anything. For now, there is a number. So we don't want to make an entire number split into tokens, 2 and then number 0. It won't make any sense. What we want is we want 20 entirely. It will make our job very easier. So after converting this line of code into tokens, it is now easier to manage. We have type integer, then we have identifier X, a sign of equal to, and then there is a number. Now to add rules to this, before an ID, there should be a type. If there is no type, it should be defined in lines above this one. Or let's say after integer and after a type and an ID, that should be equal to sign always. If not, it will give us index error. Or let's say if there is a type integer, then after the equal to sign, there should be a number. So this checking can be done. The syntax errors checking can be done using these tokens. It is very difficult to do that while it is in the raw string format. Let us consider this example. Let z equals to 20 plus 40. Now we did tokenization before and we got this array of tokens where each token is stored into a separate index. Let z equals 20 plus 40 and then we have a semicolon. Now let's say we want to evaluate this in and assign 20 plus 40, that is 60, to the variable z. How can we do that? Let's say we wrote a program which goes left to right and evaluates the array. So we will first find the letter. We will find the token let. Now because we found the let, we expect there should be an identifier because this is an assignment token. So we will check and yes, Z is an identifier. After an identifier, we need an equal to sign. Yes, it is also present. And after an equal to sign, we need some literal. A literal is nothing but a static value which does not change, which we have a 20. So now let Z equals 20 is a valid equation for us. We can evaluate it as of now. So we will make a variable Z and assign value 20 to it. Then we encounter a plus sign. Now, after an assignment operation, plus sign is not a valid thing which we can do. So it will throw an error. What we actually want is we want to first evaluate 20 plus 40, which equals to 60, and then store state 60 into the variable z. This is not left to right or right to left. It is based upon the priority. That's why we need abstract syntax trees. What it will do is convert these tokens into a tree-like structure which helps us to prioritize some operations before others. So let's say in this, we first want to do this 10 into 2, that is 20, and then add 2 to it. What if we went left to right? We will first add 2 into the 10, so we will get 12, and into 2, 24. The ordering matters here. So that's why building an AST should be our goal. We encounter an x and then we encounter equals to sign. Now for now, we know that x is equals to something else. So we will make an AST something like this, x on the left side and equal to and rest of the things on the right side. We don't know what is on the right side yet. Then we will find we have an open bracket and this is another term and this is another term. We will try to implement again an EST to it. So after an equal to sign here, we will add a multiplication sign because brackets are there on the both side. So it should be multiplied first. In this case, here is x and then two parts. We still have not evaluated these two parts. So it will be as is. This way, we go down entire tree and we try to make an abstract syntax tree. For this line of code, the abstract syntax tree should look like this. Now we have constructed the abstract syntax tree and now we want to parse the entire tree, find the value of x. To evaluate this tree into some final value or to collapse this tree, we will start from the root node and make our way downwards. First, we encounter an equal to sign. On the left of it is x and on the right of it is some other thing. So we definitely know that we have to assign x with something on the right. Right is not a value literal which we cannot assign. It is a tree. So we need to do that again. We step down and we evaluate first the multiply sign and then we assign the result to x. But multiply sign is again, it is not literal at the end. We need to evaluate this first. So we will do 40 minus 5, which we get 35. Then again, 2 plus something multiply, which we cannot do. 2 plus multiply is not a value operation. It is again a tree, so which we'll evaluate first. So 10 into 2, which we will get 20. We'll then send a 20 here. So 2 plus 20, which will be 22. 22 and multiply by 25, which will get the answer, and we can assign that number into our variable. This is again a diagrammatic representation of what we actually did. So first we multiplied 10 with 20, we gave the result here. Now because both of these are literals, we can evaluate that 40 minus 5 is 35 and 20 plus 2 is 22. And finally we can multiply it. After multiplying, which we can store it into our variable x. To recap, we saw how we can convert the code into tokens and why tokens are necessary. We saw how we can convert tokens into abstract syntax trees, which we again saw how ASTs are necessary, and we saw how to collapse the ASTs. So this is just the overview of making a programming language. After collapsing, there are multiple things: making environments, managing variables, garbage collectors, foreign function interfaces, lots of things. We will try to cover this one by one. In next video, we will try to dig deeper into how we can convert code into tokens and how to write the code.